Okay, so now we're going to start talking about more general models of computation. So up until now, we've been mostly talking about weight-free read-write memory. And weight-free read-write memory is a lot of fun because historically that's what people have looked at. But if you go out and buy a laptop, what you get isn't weight-free read-write memory. You get a much more complicated model where you have compare and swap operations and you have timing constraints and things like that. And so we'd like to be able to take some of our results and apply them to these more sophisticated models. And so what I'm going to do is I'm going to talk about the notion of an adversary, which is a kind of general way to talk about failure models. You can encompass failure models into a different structure. And we're also going to focus on round-based models, where we're going to take the computation and break it down into smaller rounds. That way we can argue inductively. We can take a complicated model of computation, break it down into simpler pieces, and then argue inductively about the simpler pieces. Pretty much everything we're trying to do here is take big complicated stuff and break it out into small pieces and reason about it in a reasonable way. And so to do that, we're going to need a combinatorial notion called shellability, which is another something that we pulled out of the classical textbooks. And once you learn about this, then you'll see shellable complexes everywhere you go. We'll prove a nice theorem about how shellable complexes behave under carrier maps. And then for applications, we're going to go through and talk about the various different models here and how we can use kind of a single big theorem to reduce reasoning about these models, which superficially look very different, to almost the same thing. So this is kind of a grand unified theory of different failure models. So we started out looking at weight-free computations where all but one process can fail. So models in which everybody can fail aren't very interesting because you can't really solve very many problems there. And so the strongest reasonable constraint you could say is, well, as long as one process is still working, we want an answer, a correct answer. But you can say, well, that's kind of harsh. It's a very strong requirement. Google has millions of servers, and they don't write algorithms that keep working if 999,999 of them fail. They don't expect to have more than 10% down at any point. And so you can say, well, what I really want is something we'll call T-resilient. That is, you'll tolerate up to T failures, where T might be, say, 10%, 80%, whatever. So T-resilient says that less than or equal to T processes can fail. And this is also something that has been studied a lot in the literature. But if you look in the real world, once again, if you're worrying about building fault-tolerant systems that actually have to work, T-resilient is kind of a naive model for the world. That is, because failures are not, in fact, independent. So, in fact, what you might get is failures that look like this, where, say, these two might fail, or this one might fail, but it's not the case that any other set of processes could fail. So why could this happen? Well, maybe those two processes live on the same server. Maybe they run the same buggy version of Windows. Maybe they're on the same side of a flaky network connection. But failures don't necessarily happen in an uncorrelated way. And so we'd like to be able to reason about these sorts of situations. And in particular, you might say, well, these two might fail together, but I know that the purple and the red will never fail together. Or if they do, then we're in big trouble. And so we'd like to be able to talk about models where we know that some things fail together and other things don't fail together. So in order to do this, we're going to introduce the notion of an adversary. This is something that comes up fairly often in security protocols and so on. But the idea here is that we have there's something out there that chooses what failures happen, and in some models the adversary gets to choose the interleaving and scheduling. So in an asynchronous model, the adversary can choose the timing. In synchronous models, everybody runs together, so the adversary can only control failures. And so typically what we'll have is we'll have an adversaries have to are restricted by certain rules, but subject to those rules, they can do whatever the worst thing for your algorithm is. And this is the approach that we want to take in general. So the easiest way to specify an adversary is what we call faulty sets. So we'll say the adversary is allowed to fail these two processes if it wants to. The adversary is allowed to fail that process if it wants to. So you can just list the set of processes that adversaries are allowed to fail. So one can fail or the other, but maybe that's it. So the adversary is restricted, but subject to these rules, it can be as nasty as it wants to be. Now, one assumption that we're going to make is that failure sets are closed under containment. So if the adversary is allowed to fail these two, then it might decide to fail only one. So even if these two live on the same server, it's possible that we want our program to work if they happen to be moved to the same server, or if one of these things crashes by itself and the other one keeps running. So it says that if both of them can fail, then only one of them can fail. Now, this is something that, believe it or not, people argue about. Were you at PODC?
I missed the discussion.
Oh, yeah. No, Ellie got very upset about this. There's an alternative which says that, you can say, well, we have a model where this isn't true, where if both of these can fail, then if one fails, the other must fail. This was Ellie's argument so we're going to reject this as a reasonable model because we don't want to ever require failures. And the reason this is a really bad idea is because you can come up with really pathological cases. And so, for example, suppose I tell you that the failure sets are all but one process. Then you can solve consensus. Why is this? Well, I know that eventually everybody but one person is going to fail, so I just wait until everybody but one person fails. And then if I look around and see everyone else has failed, I decide. And this is maybe a lot of fun, but it's hard to convince funding agencies that looking at these kinds of problems is interesting. So we're going to assume that failure sets are closed under containment. So, yes?
Also, it could be possible that you could sort of do something with the two failures, but a single failure may be more, is it possible that can be more dangerous? Like if just one failure happens, some problems can be more complicated.
Well, it's true that if you knew for certain that someone was going to fail, that some problems are paradoxically easier to solve. Because if I see that A failed, and I know that if A fails and B fails, is certain to fail, then I can ignore B, and it's not going to cause problems. But if I don't know that, then there's still more uncertainty. And so we're rejecting this approach mostly not because it makes things harder, not because it makes things easier, but because it just seems unrealistic to say that I know for certain that someone's going to fail, so I'm just going to sit there and wait for them to crash and then proceed. So this idea of being closed under containment sounds familiar. So we're going to represent failures as a simplicial complex. We're going to represent adversaries. An adversary itself is a complex. There's an old statement that if your only tool is a hammer, then the world looks like your thumb. So that's what we're going to do here. So failure complex, we have, each vertex is a process. And I'm going to draw a simplex joining processes if those processes are in a failure set together. This is it's possible for both of them to fail. And the rule about inclusion means that this is a simplicial complex. If this is a simplex, then so is each individual vertex. And so we need, otherwise this doesn't work. So a weight-free failure complex is just the skeleton. You can't fail all three of them, but you can fail any two out of the three, and that's the one skeleton of the two simplex. So basically, the n-1 skeleton is the weight-free failure complex. Yeah.
What if the blue, I mean, if you have these either the red and green fail or the blue fails, then it's a disconnected?
Then what would happen is that you would have an edge between these two guys because that's a failure set. This vertex would be isolated, so then it would be disconnected. Yeah. So T-resilient is a T-skeleton. So in this case, let's say that one process can fail. Oops. So let's say that only one out of three processes can fail. Then that's this disconnected skeleton because there's no each vertex is a simplex, but nothing else. So now I'm going to define a. So working directly with failure sets is going to be tedious. So I'm going to introduce two notions that kind of summarize everything you need to know about adversaries. So which are cores and survivor sets. Now these don't uniquely define an adversary, but we're going to show that that's all that matters. That adversaries with the same set of cores are equivalent, computationally speaking, even if they're different adversaries. So what is a core? A core is a minimum set of processes that cannot all fail. So operationally, it says that if you pick a core and you wait for some one of them to show up, that will always happen because they can't all fail. So you're allowed to wait for some member of a core to show up. So it's safe to wait for a member of a particular. You can pick a core and then wait for some member, at least one member of that core to show up. What is a core in terms of the failure complex? Well, a core is a minimum simplex that is not in the failure complex. So basically, it's any simplex that meets. This edge here, for example, is a core because it's it's minimal dimension. Anything smaller is a failure set, but it's not a member of the complex. So we can define cores in terms of this failure complex. For the weight-free failure complex, what are the cores? What is it safe to wait for in a weight-free world? None of them. So in a weight-free world, the only core is the entire set of processes. So you're right. You're allowed to wait for all of them, but since you're already there, you can't. You wait for none of the others. Is what I should have said. So what you said was correct. So this is the only core in the weight-free world. In T-resilient world. This is one resilient. Any set of T+1 processes is a core. So any T of them can fail. So you pick any set of T+1 and you wait for one of them to show up. That's okay. And so that's any T simplex is a core, because T contains T+1 elements. So we can define these things combinatorially. And so it turns out that basically all the models that we're going to look at, I don't know whether this is true of every model you could come up with, the minimum core size completely determines the adversary's ability to solve any colorless task. So the only thing you need to know about an adversary, if you want to know what colorless tasks can I solve, is what's the minimum core size. And there's you pick a particular core size. There's a huge number of adversaries that have that core size, but they're all the same, as far as we're concerned. This is not true for colored tasks, because colored tasks you're allowed to discriminate between nodes, and core size doesn't work. But if your task is colorless task, then a core size is all you need to know, for the models that we'll be looking at. And for all I know, it's true in general, but I can't be sure that somebody can't come up with a pathological case. So this is the, so if you want to go and buy a distributed system from, IBM or Raphael or someone, then you should ask them, what's your minimum core size? So there's a dual notion to core size, which is survivor sets. So cores and survivor sets encode the exact same information, but they're in different forms, and sometimes it's convenient to use one and sometimes another one. So a survivor set is a minimal set of processes that might all survive. So what does this mean in terms of writing an algorithm? It means that if you want, you could set up a barrier where you wait for other processes to show up, and you can wait until a survivor set shows up. You're guaranteed that a survivor set will always show up. Every member of a survivor set will show up. Once the survivor set has shown up, then you better not wait anymore, because you're not guaranteed that anybody else is ever going to show up. But you know that some survivor set will show up. So you can see that this is kind of a dual of the notion of a core. So it's safe to wait for all members of some survivor set to show up.
So you can condition on all possible survivor sets and wait for one of them to
Yeah.
complete. So
Yeah.
this is equivalent to, for example, waiting for n minus t process.
Exactly, yeah. Yeah.
Statistic algorithm.
Yeah, that's exactly the way to think about it.
Just for clarity, this is like after one attack of the adversary, right?
Well, the adversary is, this is all the failures it can do during the entire computation. So the algorithm might be round by round, but the adversary over its entire lifetime is not allowed to fail all members of a core or keep you waiting forever for a survivor set. So on every round, you can wait for a survivor set, and there might be different survivor sets. But you always know going forward that eventually some survivor set will continue to take steps, because you can't fail every, some survivor set has always got to be alive at every point.
So you take sets of all n minus t sets.
Yeah, yeah. But for adversaries that are asymmetric, for example, then you might have a more complicated description. So this is really an abstraction of that notion. So instead of saying it's uniform, that it's n minus t, we'll say that it's just some collection of sets that have this property. But it's going to look very much like t-resilient computation when we're done. So we'll leave it as an exercise. If I give you the set of survivor sets, then you can compute the set of cores and vice versa. So these are completely redundant ways of pieces of information. Sometimes it's convenient to use one, and sometimes it's convenient to use the other. So we're going to go back and forth between them all we want. So in the failure complex, what is a survivor set? Well, a survivor set is you take a failure set and you take the complementary simplex. So here, this is a failure set, that's a survivor set. Because it's possible that these guys all fail, but if those guys all fail, then this one will survive. And in fact, vice versa. That this is a survivor set, and that's a core. So for weight-free failure complex, any individual process is a survivor set. Because some process has got to survive, but we don't guarantee that any more than that survive. So any vertex in this complex is a survivor set. T-resilient, any set of n minus t plus 1 processes is a survivor set. Again, the plus 1 is because we have n plus 1 processes instead of n. So in that case, any n minus t simplex is a survivor set.
The survivor set doesn't have to be simplex inside?
In this, no, each individual survivor set is just a set of processes which is a simplex of kind of the complete complex on all of these things. But it is not necessarily simplex of the failure of the adversary complex, of the failure complex. In fact, it's typically not. In fact, I think it's, yeah, a core is always not a simplex, but a survivor set might be. Okay, so that's the notion of an adversary. So this is all kind of motivation. You know, this is the part of the world that we want to deal with. And so one of the things that we do here, remember before when we talked about the connectivity of processes, we had this critical state argument. So we said that, well, we know eventually things are connected. Let's assume by way of contradiction they aren't. We move everything into this critical state and then show that it breaks down, and then by contradiction it must have been connected all the way along. And so we start out, we assume it's not unconnected, we get a critical state, show that afterwards it's connected, and then we get a contradiction from that. And this is sort of one of the oldest styles of reasoning in, for showing connectivity and impossibility, but it has its limits in the sense that it works really well for weight-free read-write memory, but then it starts to get difficult to use when you go to T-resilient, and it's, as far as I know, it's either impossible or impossibly difficult to, or impossibly awkward to apply it to the synchronous world. So what we're going to do is we're going to look at a different style of a proof. So limitations works best for a synchronous model. So the biggest problem is that if you look at the critical state analysis, what we're saying is, well, you know, suppose that P is doing this and Q is doing that, then we derive a contradiction, say, suppose instead they're doing something else. And so the number of cases you have to look at becomes, you know, really big. So suppose I want to do a critical state that says that if I have read-write memory, test and set, and a case set agreement box all together in the same system, then you can't do a consensus. Well, you've got to go and analyze each one of the 2 to the n possible interactions. And that, you know, that gets kind of boring, even when it works. So instead, we're going to do invariance proofs of connectivity. So I'm going to say this is k-connected, and I'm going to analyze each step and show that if it's k-connected before, it's k-connected after. And that is going to make life easy because I can take each step. If I want to mix all these exotic things, I can say, well, I've got if I have a step that is only read-write, then this is true. If I have a step that is only case-set agreement, this is true. I glue them together, and because it's invariant, it's true. So you get something that where the proofs are much simpler, and it's much easier to mix and match different pieces of models in an invariance argument. So we're going to do round-based models. So we're going to break computations into sequences of rounds. So in synchronous models, rounds happen at the same time. So we're going to say, okay, so everybody takes a step, this happens. Everyone takes a step, this happens. In asynchronous, the same round can happen at different times. So I can take my first step, and then a year and a half later, you can take your first step. And they're both the same round, even though they might not take place at the same time. And we're going to show that connectivity is an invariant. So we're going to look at the details of the model and say that this round preserves connectivity, and therefore we can string these together for as long as we want. And we will have no critical states or contradictions. So this is more of a positive kind of argument. And so what this is going to look like is I'm going to start out, we're going to argue that if the initial state is k-connected and nice, we'll define nice later, and the round map has a particularly nice local property, then the complex is still k-connected and nice. So we need to have k-connectivity will be part of the invariant, but we'll also need something else that will basically keep the induction moving. So this nice and this nice aren't going to be the same property, but they're going to have to fit together. And so that's our strategy. And so then by pushing these things on, we'll be able to show that the entire computation is highly connected. And then we'll use that connectivity for lower bounds. So I think I'm going to stop there because that's sort of the motivation for what we want to do next. And we'll show you how to actually do that next time. I'll have some more pictures for you.